Hi Saints, this is Mr. Matthew Lim. Today I'll be delivering the fourth lecture on gravitational field. We will focus on the four objectives that we have already done before. Today we are going to strengthen our applications of the concepts. So focus on the four equations that I've written down here. We want to see uh, how these four equations can be represented in the form of a graph. So let's look at the first one. The first one is this equation which you need to memorize. However, I need to remind you that this is the vector form of Newton's law of gravitation. So most of the time in calculation, we will drop the negative sign. All right. So this law is an inverse square law. As you can see, Fg is proportional to minus 1 over r square. So what you need to know is the shape of the graph. The shape of the graph is curving um, upwards towards the horizontal axis. And the area of this graph represents the um, change in the potential energy. Okay, so as the body moves from, let's say, from one point to the next point, then there is a change in the gravitational potential energy. Okay, then on the right, we have the graph of G versus R. So the equation is G equals to minus Gm over R square. Again, let me remind you that this is the vector form of the equation. In problem solving, most of the time we are interested only in the magnitude, so we drop the negative sign. So the area under the G versus R graph uh, is actually the change in the potential. Okay, so as the body moves from one point to the next point, so there is a change in the potential. So memorize the two equations, and some of you may be wondering, where does this equation come from? It actually comes from the topic of WEP, and you can refer to equation 5.9. Okay, equation 5.9 of this topic WEP. So force is the negative potential energy gradient. All right. So similarly, field strength is the negative of the potential gradient. So let's look at the other two equations. Let's start with the one on the left. You have to memorize this equation. This time the negative in this equation is essential because gravitational potential energy is always negative except at infinity where the value is 0. Okay, so I want you to look at the shape of the graph. It looks like the one above, but this time the graph is more gentle. So suppose I compare this with the graph of the gravitational force. So you'll find that the graph for the gravitational force Fg is steeper, okay? The one that you see on top, okay? This graph is steeper compared to the one of the potential, compared to the U graph. Fg compared to U, Fg is steeper than U, all right? And then the gradient, in fact, I should say the negative of the gradient represents the force. So at any point, the negative of the gradient represents the force on the body at that particular point. And then we are going to look at the next one. Um, Potential equals to minus Gm over R, right? So again, negative is essential. In fact, for gravitational potential energy and gravitational potential, the negative signs are essential. You cannot just drop them, okay? Um, in contrast with the earlier cases, force and field strength, both are vectors, and we drop the negative sign because Most of the time, we are only interested in the magnitude. So here, the negative signs are essential. So the gradient of the potential versus R graph uh, is equal to the negative G, or you can put the negative on the other side. Okay, G equals to minus gradient, or you can say gradient equals to minus G, right? So you must know the relationship between um, the various quantities. Like for example, here the gradient represents G, and on the left, gradient represents the force. And then on top, we are interested in the area, all right? Area of the force versus R graph represents change in potential energy, whereas the one on the right, the area represents the change in the potential. So how do we apply this concept? So we are going to look at the next page. Now, although this is a visible thinking question, um, I will talk a little bit about this because it has direct relevance to the graph that I just talked about. So if you look at this black graph, it's actually made up of the sum of two graphs. The red one is actually the graph of phi m, that is the potential of moon, which is actually proportional to um, negative 1 over r, right? And then the blue one, okay, this blue one is actually the potential graph of the Earth, okay? So, so they curve in this manner because of the shape of the graph here, okay? So let me erase some of these so that it will not complicate things. Let me get a bigger eraser. So let me erase this. Okay. Now, you see the shape of this graph. The shape of the graph is the inverse graph. So therefore, you have the inverse graph here. All right. If you sum the blue and the red graph, you get the resultant, which is the black one. All right. It's the resultant potential. This is the resultant potential. So let me use another color. Okay. This is the resultant potential of moon and earth system. Right. So look at this point. This point, I will draw the point here because otherwise it becomes very cluttered. Okay, this point. Suppose I call this point P. This point P is actually a neutral point. Okay, let me write this neutral point. It means that at this point, the pull due to the force of gravity of the Earth is actually equal and opposite to the pull of gravity of the Moon. Okay, so this point is actually called the neutral point. At the neutral point, um, the net force is zero. Okay, net force is zero. Okay, how do I know about this? Well, you know this relation is equals to minus d phi dr, right? Okay, the gradient of the black graph represents the field strength. So right at the top, at point number 2, if you look at point number 2 here, the gradient is 0, right? So if the gradient is 0, it means that G is 0. If G is 0, the force is 0. Okay, so in order to throw an object from the moon to Earth, all right, so the body only needs to overcome the potential barrier. So what do I mean by the potential barrier? Potential barrier refers to the height of the hump. So let me magnify this a bit. Um, this is the height of the hump. Okay, the height of the hump. So if I'm able to move the body from 1 to 2, um, it means that I have to supply enough kinetic energy to overcome the potential energy between 1 and 2. Okay, so that is why I write the equation like this. Look at the equation that I write. Oh, I've minimized this too much. Okay, this is the one that I'm referring to. So the amount of energy required, in fact, this is the minimum amount of energy required to um, cause a body to move from moon to earth, because all the body needs to do is to overcome this potential barrier. Okay, so delta GPE is the potential barrier. So this is the delta GPE. So I magnify this again. I will write this as delta GPE. Okay, this delta GP. So I only need to supply enough KE to overcome delta GPE. Those of you who study chemistry, you learn something called the activation energy to cause a reaction to start, right? So there is this minimum energy required to start the reaction. So here, in order for a body to cross to the other side, that means moving from moon to earth, it must actually overcome this potential energy hump, which is delta GPE. So that is the reason why we write the equation like this. Okay, so let's move on to the next concept called the escape speed. What is escape speed? Well, before you understand this, you have to know a little bit of background. Suppose this is the earth, right? This is the earth. If I throw an object up, I'm very sure that it will come back. It will come back to the earth, right? So if I throw it higher, in other words, I exert a greater velocity, it will go higher and return, right? So am I able to supply a certain velocity, a certain velocity which is known as the escape velocity, such that the body will go to infinity. The body will continue to go until it reaches infinity with zero speed. Okay, is it possible like this? Well, we define this theoretically. So, escape speed is actually the minimum speed. Okay, minimum speed of projection that will cause the body to move away from the earth's surface and reach infinity with zero speed. All right, so therefore we apply principle of conservation of energy like this. So we start from the point earth. Can you see this body is actually at the earth's surface? So this part, the first part here, this part is at the earth's surface. Okay, let me write down earth's surface. So at the earth's surface, we actually supply a certain Ke to the body, and at the earth's surface, the body has a certain gravitational potential energy. Then next, the body will eventually move to infinity, right? Move to infinity. And it reaches infinity with zero Ke. And then you know by definition, the GP at infinity is zero. So this is how you derive the expression for escape velocity. Okay, and you are not allowed to uh, recall this equation uh, and apply it unless it is an MCQ question. So every time if you need this expression, you have to derive it. Okay, so recall is not allowed except for MCQ. So let's apply this escape speed formula to this particular example. Determine the minimum Ke needed to leave a mass of 2 kg from its surface into outer space. Okay, so what is the minimum Ke? So you have to start with this principle of conservation of energy that you have seen it here before. Okay, this one is actually the same as this one. Okay, it's the same as this one. Okay, if you compare this equation with this, it's exactly the same, right? So here you can substitute the values and obtain the minimum Ke, right? And then from the minimum KE, you are able to get the escape speed, all right? Escape speed is equal to, or escape half mve squared, okay? So minimum KE is equals to half mve squared. So the escape speed can be easily calculated, right? So you may want to pause this video and understand the mathematics of this question, right? Let's move on to the next part. Work example 18 suggests why the moon has no atmosphere. Now we know that the moon has a very low escape velocity, which is 2.4 km per second. Compare that with Earth. You see, Earth has an escape speed which is much higher than that of the moon. So every molecule has a certain speed. So we will take the average speed of molecule. So if the average speed of molecule is higher than the escape speed of that planet, the molecule will escape. So therefore, moon has no atmosphere because most of the gases have average speeds higher than the escape speed of the moon. Whereas Earth got an atmosphere because the escape speed of the Earth is much bigger. All right. The next video is an interesting video, but we have no time to play it here. It is a 12-minute video on black hole in the universe. So if you've got time during the holiday or during your free time, you may um, view this. Okay, energy of a satellite. Now, this is one of the four formulas I asked you to memorize, right? One of the four that we talked about at the start of the lesson. So this is the potential energy of the satellite at a distant r from the center of the planet. So this is the normal way of writing. Centripetal force is provided by the gravitational force. So we have already seen this before. That is, we equate the centripetal force to the gravitational force, and eventually we get the equation Ke equals to gm over 2r, right? So we have equation for Ke, we have equation for potential energy. So if you were to add the two equations, in fact, this equation we noticed earlier on, this equation is actually equation 710, right? So equation 710 and equation 714, if you add them together, you get the total energy, okay? This is the total energy. Total energy is the sum of Ke and Pe. Ke and Pe, you sum them up, right? So erase this. So once you sum them up, you get the final form. The final form, which is total energy, is equals to minus gmm over 2r. Okay, you have to memorize all these three equations so that, in fact, you don't need to memorize. You have to learn how to derive, okay? Recall of this equation may be expected in MCQ. Again, you need to derive this. You cannot just apply the equation um, unless it is a multiple choice question, okay? So derivation is required. So if you compare these three equations, now you are able to see these three equations. Then you notice that this Ke and the total energy graph are actually mirror image. These are mirror image. Okay, why is that so? Look at the equation. They are mirror image, right? So equation, this is the equation compared to this one, right? One has a negative sign, the other has no negative sign. So they are the mirror image, okay? Whereas the potential energy graph is actually lower than the total energy graph. So you have to recognize the shape of the graph and you must be able to derive equation 715. Okay, What if energy is lost to the atmosphere? You know, satellite doesn't stay in orbit forever. After a while, it loses energy and it will spiral towards the Earth and crash. That was the in the past. In the past, that is actually what happened. But nowadays, if satellite gets too close to the Earth, um, scientists will activate a booster rocket and push it out of orbit to outer space. In other words, we throw the satellite into the outer space so that it doesn't crash onto Earth and cause injuries or damages to property. Okay, so when satellite loses energy, it actually loses energy in the form of thermal energy because there is work done against friction. And what friction are we talking about? We are talking about friction due to air particles, all right? So, so when it loses energy, the total energy will decrease. Okay, look at this equation, which is the total energy equation. When this total energy decreases, when this one decreases, it simply means that it becomes more negative, right? It becomes more negative. How to make it more negative? To make it more negative, it means that R must be getting smaller, right? Because when the denominator becomes smaller, then actually the magnitude becomes bigger. When the magnitude becomes bigger, the total energy become more negative, right? More negative. So actually the satellite gets closer to Earth. Okay, when decreases, it means that satellite is closer to Earth. Okay, so now if you look at the kinetic energy formula, the green one, look at the green one. So this is the green one. So what happens if R decreases? If R decreases, actually KE actually increases. Okay, actually, so it's rather strange. Um, you know, on one hand, we say that the satellite loses energy, and on the other hand, we say KE increases. Well, it can be explained. I can write this equation, E total equals to KE plus GPE, right? Okay, this is actually what happened. You know, when satellite loses energy, E total decreases, right? E total decreases because GP decreases more. GP decreases more, but there's an increase in KE. Let me write it again. There's an increase in KE, okay? So because GP decreases much more than the increase in KE, there is a net loss in total energy, okay? The net loss in total energy actually goes into thermal energy, okay? So we come to the last example for today. A satellite orbits a planet at a distance r from its center. Its gravitational potential energy is negative 3.2 megajoules. Another identical satellite orbits the Earth at a distance of 2r from the center. What is the sum of the KE and GPE of this satellite? So, as I told you just now, you have to memorize the equation, right? So, this is the potential energy equation. You are told that it is equal to minus 3.2 megajoules. And then just now, I told you that we have to learn how to derive the KE. So you have to learn how to derive this, and you have the KE expression, and then from the KE expression, you derive this expression for total energy. So all these in yellow, you must know how to derive. And then now you compare the expression here, total energy of the second satellite with the first satellite. Okay, suppose this the yellow one is for the first satellite. So for the second satellite, the distance is 2r. Can you see this second satellite? The distance is 2r. Okay, the first satellite, the distance is r. Okay, so take note of here. The distance is r, the distance is 2r here. So now you have to pause the video to see how these mathematics work out. So you notice that if I bring the 2 out of the equation, I get a quarter here. And then I have this minus GMM over R, which is actually 3 minus 3.2. Eventually, the answer is minus 0.8 megajoules. Okay, so um, okay, this is the gravitational potential energy. Also, in that case, I think this is not relevant. I erase this. This is not relevant. So, okay, so a satellite, when you bring it up, the distance is 2r compared to the first satellite where the distance is r from the center of the planet. So that is how you get the total energy, because over here is stated the sum of Ke and GPE. So this refers to the total energy, okay? This is the total energy. So you want the total energy, and the total energy is actually calculated here. Okay, so that's how you solve this. So you pause this video to understand the mathematics. All right, we have come to the end of today's lecture. So there's one more example, work example 20. You have to go through the example yourself, because this is to train you in your thinking process. So work example 20 is for you to exercise your thinking, right? So at the end of the lecture, always go through the assessment objective to see whether you know how to apply the concepts that are laid before you. Okay, that's the end of today's lecture. Thank you for your kind attention.